Good morning, or maybe good afternoon, depending on where you are joining us from today. On behalf of Bartlett and West, I want to thank you for joining us today. We are really excited to be able to offer live webinars to engage our subject matter experts as they share their knowledge and expertise. Our webinar today is going to be 30 minutes in length, along with time at the end for Q&A. During the webinar, please send your questions through the chat box, which is in the lower portion of your screen. Your questions will be monitored throughout the presentation today. We will be issuing PDH certificates for those attending the live session that have elected to receive them, and we'll be sending those out within 24 hours. We do encourage you to visit our website at www.bartlettwest.com and click on the Webinars tab to see upcoming webinars as well as to register. All of our webinars will be available on demand after the live session, so we certainly hope you can join us again. Today we're going to hear from James Kroonlead. James is a U.S. Navy submarine veteran who specializes in energy-related projects such as biogas CHP and biogas upgrading systems. He has experience leading multidisciplinary teams of engineers and designers on pump stations, standby power systems, and anaerobic digester projects. He's going to be discussing the benefits and opportunities of biogas treatment upgrade projects. And so without further ado, I'm going to turn it over to
Thank you, Rebecca. Can you hear me okay?
I.
Okay, thank you. And thank you very much for that introduction. The first thing we wanted to do is gauge a level of understanding on biogas from everybody by running a quick poll. You can see on your screen, just trying to get where everybody is on this subject. I know from the sign-up list that there's probably a few people in here that can answer the fourth one. I know a lot more about biogas than you do. And if you answer the third one, my plant has a digester, but we're not sure what to do with it. Marketing has told me I have to ask you to give us an email and a little bit more information. So I appreciate everybody taking the chance to fill this out. And I appreciate everybody turning off Tiger King long enough to watch a webinar. So thank you very much. Are we still having audio issues, Rebecca?
It looks like there's maybe an issue. I'll try and handle it with the one participant. So you can.
No worries. So we're going to go ahead and get started. I'm just going to give you an overview of what we plan on talking about today. I'm going to give an overview of biogas sources, different places where biogas can come from. And by that, I mean, I am counting digester gas, landfill gas, and all of those and lumping them as biogas. We're going to talk about methods to increase our biogas output, what to do with the biogas when we get it, and biogas upgrading, cleaning up the biogas to reduce O&M costs and also to add revenue through renewable natural gas. So let's first talk about biogas sources. So on the screen in front of you are 4 different sources of biogas, kind of representing a broad range of industries. Upper left-hand corner, that's a fully mixed digester at a wastewater treatment plant. At the upper right-hand corner is a covered lagoon digester at a food processing plant. On the lower right-hand or lower left-hand corner is a plug flow digester at a dairy in Wisconsin. And the bottom right corner is a landfill. All these have different benefits, especially the different type of digesters. There's positives and negatives for using each of those types. That's probably a whole nother presentation, but that's a general idea of where we're getting biogas from. So what actually are we talking about when we say biogas? What we're talking about is we're taking biodegradable material, wastewater sludge, liquid waste, solid wastes, waste from dairies and things like that, and putting it into a tank, or this goes underground in a landfill. Anaerobic bacteria break down um, that waste and produce biogas. The solids come off and can be used as bedding or fertilizer, depending on what the rest of the process looks like. We're going to focus really on the biogas. From that biogas, we can do upgrading to natural gas, renewable natural gas, combined heat and power, or boilers typically. Now, what is actually in the biogas? The main component of biogas is methane, and the one that we're really concerned with. Methane's the same thing that's in natural gas. Typically, we're between 55 and 65%. I've seen some a little bit lower, a little bit higher, but that's generally a good rule of thumb. Carbon dioxide makes up the balance for the most part. Um, Generally, we don't have to do anything with that if we're using it in an engine or something like that. But if we're going to use it in renewable natural gas, we'll have to pull that part out. Oxygen and nitrogen typically exist in trace amounts. We try to, you have to be really careful when you sample because sometimes you can, hey, your samples can show you that you have oxygen or nitrogen, and really you just didn't do the sample right. Hydrogen sulfide is one of our bigger contaminants that we're worried about. It's a poisonous gas and can be very corrosive. Some plants are as low as 50 parts per million. I've seen plants at 500 or 5,000 parts per million and above. Now, siloxanes and VOCs, there's some people on here who said they weren't all that familiar with the topic. Siloxanes are a organic silicon compound that's used as a binding agent in cosmetics, deodorants, soaps, things like that. It's completely inert and really a pretty great product until you put it in a digester and it comes off in the digester gas and you try and burn it. When it comes off in the digester gas and you burn it, it turns into silica oxide, which is sand. And most engines and turbines and anything else really just don't like sand. So we have to try and get rid of that. VOCs, that stands for volatile organic compounds. You may have heard that on like paint commercials and things like that. VOCs can really vary from plant to plant and landfill to landfill. It really has to do with what kind of things have gone into that plant and what kind of treatment processes you have. Uh, you might see acetone, toluene. I've seen octane. Um, it really just depends on the what is the going into that plant. Now the gas is also typically saturated, meaning it's 100% humidity, so there's lots of water in the gas. Now, one way to boost your gas production is to add um, additional waste to your digesters. Um, Now, to do this, you have to have excess digester capacity. So if you're a wastewater plant, you have to have enough digester capacity to meet your requirements, your discharge requirements, and have a little bit extra. If you have a little bit extra, you can add fats, oils, and grease, which is pumped grease trap waste. Typically, the average person produces about 13 and a half pounds per year. So there's plenty of that out there. There's also, you can read on here, there's lots of other types of waste. I've seen brewery waste put into wastewater digesters. Um, the picture that you're seeing on the screen is actually a fog receiving station at a wastewater plant in Oregon that has a 20,000 gallon tank, the white one, and the green one is a 10,000 gallon tank that we are taking probably a lot of the fog from the Portland area and putting them into these tanks and feeding them to their digesters. That's going to come into play later, but I'll save that for the later slide because that'll be important. One of the first things, so biogas utilization, there's a few different things we can do to utilize the biogas after we're generating it. First thing is boilers. All digesters typically need heat. They're typically heated to about 95 to 105 degrees, depending on the type of digester. Some are a little bit higher. So you almost always need heat. You can also do CHP or cogen, which is producing both electrical power and heat. Or sometimes I've seen power then used to run a engine driven blower or something to that effect, but a power and then a heat component. You can also upgrade that gas to natural gas quality. There are incentives with the renewable fuel standards, the similar legislation or the same legislation that the ethanol industry runs under, that make it beneficial to produce renewable natural gas from biogas sources versus and then maybe even buy regular natural gas because of the environmental attributes associated with that gas. One of my colleagues will be giving a presentation in the next month or so that will go into much more detail on that subject because it's really something that really deserves a deep dive. On the screen you see here, this is a dairy digester facility, or a 3D image of a dairy digester facility in Wisconsin with the walls removed so you can see everything. If you have any questions as we're going, please just type them into the chat box. First thing we'll talk about here is boiler use. So boilers can be used to provide heat for the digesters and the rest of the buildings, which may be a huge load depending on where you are. One concern with using digester gas in a boiler is some of those contaminants, like I mentioned siloxanes earlier. If you look at this picture on the left here, which was provided by Unison Solutions, so thank you for that. This is a picture of boilers that have a lot of siloxane damage. Now you can see the siloxanes form sand when they're burnt, but then they condense out onto these tubes and make glass essentially, and glass is a really good insulator, and that's not good for boilers. This other picture is a boiler in a wastewater plant in Duluth, Minnesota. Now at that plant, they don't have enough biogas to meet all their heat needs in the winter because it's in Minnesota. So the other thing we can do with it is we can do combined heat and power. Now, one of the benefits of combined heat and power is that 3 to 4% of all energy generated in the United States, and this may be a little old of a statistic, is used to convey and treat wastewater. So anything we can do to reduce the amount of energy needed to do that is a benefit. We can take gas that's typically flared and run it in what's called a prime mover. Every CHP system or cogen system has a prime mover. That can be an internal combustion engine, same thing that's in your car, unless you have a diesel. A microturbine or a gas turbine. A microturbine is kind of a smaller version of a gas turbine, to be very basic. Gas turbines are basically jet engines. So a lot of these pieces of equipment are going to require gas treatment. There are some other types of prime movers, but those three are really the biggest ones that are in use, to my knowledge now. So I wanted to go over an example of why you would do CHP. So I mentioned earlier, I showed you that fog receiving station and said that that was important and you should keep that in your mind. Well, a plant that I worked on in Gresham, Oregon, a smaller plant, 10 MGD, added that fog receiving station. And they also added two 800 kilowatt CAT engines, or two 400 kilowatt engines for a total of 8. Now, along with a bunch of energy efficiency measures, they've actually done where they've produced enough biogas from adding the fog and food waste, or the fog, to run both of those engines at 100% and become net zero. And that happened back in 2015. So, I mean, 5 years ago. So they're probably even better now. That's something that you can do with your plant. That if you add enough of that excess waste, generating enough biogas to achieve that is something that's available. Now we'll talk about internal combustion engines. These are basically, like I said, just like what's in your car, just quite a bit bigger, obviously. Um, Now you can run engines. There are engines that run without any gas treatment or with minimal gas treatment. They have a lot of maintenance issues, especially if they have a heavy amount of contaminants like siloxanes and VOCs and H2S. The picture in the center here is a cylinder that's been exposed to a lot of siloxanes, and you can see that the glass has plated out onto these the valves and onto the head. I've seen cylinders that have actually blown through and exploded because they've worn so much and the heat builds up so much in these that they can fail. One of the benefits of doing gas treatment for an engine is I've seen engines where they were changing out spark plugs and doing no major overhaul every 2,000 hours and reducing that to once a year. Now, on some of these engines, like this Janbacher engine up in the corner here, those spark plugs are $500 a piece. And I believe this is a 12 cylinder. So there's a lot of spark plugs, and they have to change those every 2,000 hours, and that can get pretty expensive. After adding gas treatment, they were back at 8,000 hours, so once a year. The other technology that we use typically on smaller plants is microturbines. Now, microturbine is uh, about a basketball-sized turbine, gas turbine, that spins at 96,000 RPM, really fast. Actually has air bangs. It's a really cool machine. But as you can see, it's not that big. These two machines are 65 kilowatt microturbines, and they're in West Lafayette, Indiana. Um, Above here is the gas treatment system that feeds those engines. Now, one benefit of the microturbines is their emissions are quite a bit, 10% of what an internal combustion engine is, but they require significant gas treatment. You have to treat your gas. You can't have any siloxanes. You can't have any VOCs. All the H2S has to be pulled out. Uh, but they incorporate well into a plant hot water system, which is how these are hooked up. One of the other technologies you can use, and this is on larger plants, is a gas turbine. This is more of a small jet engine, basically, not on a jet, on the ground. So this installation, the picture that's shown here, is outside Omaha, Nebraska, which is where I am, um, at an ethanol facility that is co-located with a feedlot. And in the feedlot, they have 25,000 head of cattle. So you can imagine what it smells like when you open your truck door to get out of that place. It is wonderful. Um, this plant actually has two 4 million gallon digesters and produces about 2,500 cubic feet a minute. This turbine actually makes 5 megawatts. Uh, this is obviously in construction, so this is not a completed picture, but this turbine provides all the power for the ethanol facility. It's a smaller facility, and we're actually making steam, 150 psi steam, through a heat recovery steam generator. And that actually provides about a third of the steam necessary to run the ethanol plant. The question is it cogen? Yeah, I'd say that, yeah. So you have the turbine here, and then once it's completed, or once it was completed, the exhaust ran in through the heat recovery steam generator. And this is just a boiler, basically. And instead of having um, fuel burned and run through the fire tubes, it has the exhaust coming out of this turbine is 1,100 degrees Fahrenheit, and it gets cooled going through this heat recovery steam generator and gives up its heat and produces steam, which is then sent through the plant and recycled where it can be. Did that answer your question? All the gas. Yes, all the gas recovery is from the feedlot. That's correct. The there's 2 huge digesters and 25,000 head of cattle. I believe, well, maybe I should add in, I think some of the ethanol waste goes into that process as well. So maybe I shouldn't say all of it. The next thing I wanted to talk about, Steve, did that answer your question? Thank you. The next thing I wanted to talk about, and if anyone else has a question, please feel free to type it in there. Um, this is much better. I prefer presenting in person where I can interact with people. Um, but obviously it's hard to do when we're all socially isolated like this. Um, I want to talk now about biogas upgrading systems. Now, I talked a little bit I talked at the beginning about the different components that are in biogas. The hydrogen sulfide, the VOCs, the siloxanes, moisture. We have to pull all of those out. Now, we have to pull out hydrogen sulfide and moisture, VOCs and siloxanes for any cogen system. CO2 removal is typically, we have to pull that out to use it in renewable natural gas. Now, we'll also talk a little bit about compression and flares. Now, the picture you see in front of you is a system that has both a biological hydrogen sulfide removal system, which is the large tower in the front, and a media-based hydrogen sulfide removal system. And this is actually in Reno, Nevada. So the first step typically is hydrogen sulfide removal. Why that's the first step is a lot of the media involved in hydrogen sulfide removal wants the gas to be saturated, wants that moisture in the gas. So we put this at the beginning of the process in order to take advantage of that fact. There are several different media that you can use. Typically iron sponge, we see a lot. Ferrosorb, I've done a lot recently. You can do activated carbon. The problem with that is it's quite a bit more expensive than the other media. You can also do biological treatment. Those are generally on bigger systems. The problem with the biological treatment when we're doing the natural gas systems is it introduces oxygen. Even at trace amounts, most natural gas pipelines won't allow those in their system. So we have to be very concerned about that. Now, there's also combination biological and chemical systems and then chemical scrubbers. The next thing we need to do is to pull out the moisture from the gas. You have to pull out the moisture to do renewable natural gas, and most combustion products or combustion engines don't want any moisture in there. Biogas is saturated, as I said before. It works out to about 4 pounds for every 1,000 cubic feet of biogas. That's a very round number, but that's generally what you can expect to pull out of biogas as you cool it down. We typically cool it down to about 40 degrees using glycol, a chiller of some sort, and then typically reheat it back to about 80 degrees for the next step in the process. The next part of the process is typically siloxane and VOC removal. The most common way of doing this, especially on smaller to mid-sized plants, is non-regenerative activated carbon. The activated carbon will be in a couple vessels. Typically, we do that where you have each vessel is sized to handle all of the flow. Once you get breakthrough through one of the vessels, you take it offline, put the other vessel online, and clean out the previous vessel. You can also do things like temperature swing adsorption, and there are some other technologies, but in a presentation like this, I didn't think I had time. Those technologies, the temperature swing adsorption takes advantage of a media and dropping the temperature to absorb the VOCs and siloxanes and then off-gas it. Again, any of these topics could probably be a deep dive. If people are interested in that sort of presentation, please let us know. Next thing, so at the point where we've gotten rid of the VOCs and siloxanes, at that point you can send it to pretty much every combined heat and power system out there. and have minimal maintenance concerns. The next part of the process is to remove the CO2, and that is for natural gas upgrading. Now, there's a few different ways we can do that. We can use a membrane, we can use pressure swing adsorption, water scrubbing, or amine scrubbing. I'll go in a little bit of detail on those. So the first system, and probably the more common system that we see on a lot of the plants that we're doing right now, are membranes. Membranes, had it described to me as it's spaghetti. And it's really thin spaghetti that you run the gas through the center of it. Contaminants go out the side. Clean gas comes out the end. You typically have to pressurize that gas quite a bit in order to get that process to happen. This is a picture of a membrane system, or a process flow of a three-stage membrane system from one of our projects. And the inset picture is a detail kind of showing the spaghetti I was talking about. Now, the number of membranes can vary. You can have a two-stage membrane system and three-stage membrane systems. The more stages of membranes, the more capture you can get, more methane capture. A three-stage system, I think, can get up to 97 to 99% methane recovery. And the gas coming off, there's a tail gas that comes off, can be vented because it doesn't have hardly any methane in it. Pressure swing adsorption is another technology. The biogas is compressed. You see on the process flow that's shown here. With this process, it goes into pressure chambers where it has media. The media absorbs the CO2. Then it can regenerate that media by dropping the pressure and causing the CO2 to come out and going to the waste gas. Very basic description of it. There's also water scrubbing. This process, you compress the gas and run it counterflow to water. So you spray water down, the gas comes up the reactor column. The water will absorb CO2 and some hydrogen sulfide from the gas. I've seen this system incorporated with some of the early fuel cell systems, which have kind of gone out of favor because they had heavy incentives to do those, and we really didn't talk about them because I haven't seen fuel cells for a while. In this system, the water is then the pressure is dropped, so the air will actually give up. The water will give up the CO2, and you can reuse that water. The last process we'll talk about is amine scrubbing. Amine scrubbing has been used in natural gas, field gas systems for fossil fuel natural gas for years. It's also the same system that we used on submarines to pull out the CO2. So I'm relatively familiar with this one. I haven't put one in to a biogas system yet, but I've definitely seen amine before. The gas comes in, amine absorbs the CO2, and then you have to heat that amine to get the CO2 out. Clean digester gas goes out to the rest of the system. Now, one part of this system that's kind of off to the side is a flare. Sometimes we have gas that doesn't meet the content that we need, BTU content that we need, or doesn't meet the contaminant specs that we have. We have to get rid of it somehow. So we'll typically involve or use some type of flare. Now, if you're adding a biogas upgrading system, you may be concerned about whether your flare can handle the higher BTU gases. That's something that always seems to come up on these projects. I see someone's typing, so I'm going to hold on for a second.
Oh. James, we did have a question. If carbon beds
I'm sorry.
For desulfurization, would that remove VOC and siloxane, or do you still need that?
The carbon bed for so yes, activated carbon will remove H2S and the VOCs and siloxanes. The reason that we usually do an H2S removal system before the carbon bed is that carbon's more expensive. So it's typically the economics work out to have a separate process to pull out the hydrogen sulfide before you get into the activated carbon. Now, if a plant, I've done plants that had um, H2S, 100 parts per million or less, I probably wouldn't bother with the upstream process. I just count on the carbon to handle it. But that's a good question. Now, once you've pulled the CO2 out of the gas, we have to compress it typically. Some pipelines, the pressure's low enough that we can take it straight to the pipeline from the pressure that we generate to get through the membranes. I've had that on a couple projects. One project where this picture came from on the left-hand corner, that gas had to be pressurized to 450 psi, typically done with a reciprocating compressor. That's what's shown there. And the other type of project, or the other use for the compressed natural gas or the renewable natural gas, is to upgrade it to compressed natural gas. Okay. What There was a question, what pressure is it pushed through the membrane? Typically 150 to 225 psi, I think, depending on the membrane manufacturer. So we'll have a screw compressor with a screw compressor, usually an oil flooded screw compressor. Actually, that's typically the biggest load on one of these systems, is that large compressor. Maybe I should have covered that. That's a comment for the next time I do this. Now, the other thing we can do with the gas is to compress it to compress natural gas, or what we do is called virtual pipeline. If you don't have a large enough pipeline to your facility, you can put it into trucks, and then those trucks can take it somewhere else and dump it into the pipeline. That's accomplished on this system here. This is from one of our dairy projects, and they're compressing the gas up to 3,700 psi to go into a truck. Now, to recap what we talked about, we went over some of the biogas sources, talked a little bit about methods to increase biogas output. Now, in the comments, that could probably be a whole nother presentation in itself. So if that's something that interests you, please let us know. Talked about utilizing the biogas in boilers and CHP systems. And we talked about upgrading to reduce O&M in CHP systems and to add revenue through renewable natural gas. The picture you see here is a 3D PDF made for a project of ours getting built in Topeka, Kansas. I removed the walls and stuff so you can see everything. We have hydrogen sulfide removal here, the membrane systems back in the back here, compression, moisture removal, and you can tell there's several different types of chillers in here to remove some of the excess heat, activated carbon in the back, and then air handling for the building. Now, the next steps here, especially if you answered on that third question on the survey, is to come look at your plant, or maybe look at your plant remotely given the current situation, and we can do a feasibility assessment to talk about what you could do with your gas. We do a preliminary engineering report and an economic analysis to see what the best way to handle the gas would be. Now, Rebecca, I just saw the question. Can you share installed cost? I don't have that off the top of my head. Let's see. I can give not necessarily a more expensive to less expensive. Flip back here. So for desulfurizer systems, Media-based iron sponge systems are typically less expensive. Um, Sulfur-treat and Ferrosorb are, oh, okay. Yeah, I'll follow up with them after the presentation, sorry. There we go. And we can do an economic analysis of the different options that we have to figure out what's the best for your facility. Now, any questions?
Thank you so much, James. At this point, um, we're going to open it up for Q&A. So please use the chat box in the lower portion of your screen for questions. We do appreciate you sharing your time with us today, and we look forward to your questions.
Joe, that's a good question. It depends on what you want to do, and there are a lot of variables that go into that. Typically, I mean, to get biogas, you typically have to have around a 10 MGD facility just to even have digesters. Most facilities smaller than that aren't going to be big enough to warrant even having the digesters themselves. For a dairy or a landfill, I mean, we're doing dairies that are on the order of 1,500 cows, and they have natural gas systems that we're putting in. The one that I showed earlier from Wisconsin is at a facility that has about 1,500 cows, makes about 225 cubic feet a minute, and has and is economically feasible. Thanks for the questions.
We'll continue to stay on the line here for a moment. Thank you so much for sharing your time with us today. Thank you, James, for sharing your expertise with us. A recording will be available on our website at bartlettwest.com. So we'll continue to remain on the line. If you don't have any questions, have a great day, and we hope to see you in the near future in another webinar.
Thanks, everybody.